couple other examples of these energy changing form would be ironing your clothes, the generator, having a generator produce electricity, the stove, cooking your food, your own body temperature at 98.6 degrees Fahrenheit, and the metabolism that you operate at. And as you can see, I've put in some values there, and so we look at ironing your clothes. You plug into the electric current and it produces heat, so it's thermal energy. So we go from electrical and we convert to thermal. And the generator, we put gasoline in. The gasoline combusts with oxygen, produces heat. So, but it also produces electrical energy. So you could put thermal and electrical here, but primarily electrical. The stove has electric energy, and the coil heats up and produces heat, so it's a thermal energy. And then, of course, your body, you produce thermal energy with your body, and it maintains that temperature. But you eat food and you breathe oxygen, and so in your cells, the oxygen combines with the chemicals from the food and produces a heat, also produces waste products. Carbon dioxide is a waste product. So you have this chemical reaction going on in your cells, and it produces heat in your body. So as we think of this energy transfer, let's reflect a little bit what we saw last week, which was on potential energy and kinetic energy. Last week we saw that there's a formula for potential energy, and it is in your book. And if you all would turn to page 266, we see that potential energy is basically the mass times G times H. So if you have an object, say sitting in one spot, you might say, well, what's the potential energy? What potential energy does this particular object have? And it's the mass, is the weight or the mass of the object. The G is the what's known as the acceleration due to gravity. Let me put that up here because that might help you understand this. Acceleration due to the gravity. And H, of course, is the height that this object is elevated. So let's say, as an example, that we had kind of doing an example here. The example is that you have, say, a 6 kilogram rock. And you take that rock and you lift it from the floor to a tabletop in your house or in a lab. And now it's sitting on the table, and you ask yourself, how much potential energy did you give the rock? How much potential energy did you give this rock? Okay, so let's write that down. By moving the rock to a higher elevation, it has the potential of falling, right? So let's figure that out. The potential energy that you just gave is the mass, and the mass is 6 kilograms. You want to multiply that by the acceleration due to the gravity, and that is a constant. It's always the same. So it's going to be 9.8, almost 10 meters per second squared. And you're going to multiply that by the h. The h, the tabletop, of course we have to give you that, I should have done that actually. The tabletop is 1.2 meters off the floor. So the amount that you just increased the height was 1.2 meters. So we have 1.2 meters. Now we multiply that out and we get 6 times roughly 10. That's going to give us 60. So this is only 9.8. So that's 58.8. And so we've got kilograms. And we're multiplying by meters. So it's kilograms, meters, all over second square. See how we did that? So we have kilogram meters over second squared. And now we're going to multiply that by 1.2 meters. Okay, so we're going to multiply the 50.8 kilogram meters per second squared times 1.2 meter. So when we do the math on that, that's going to give us 70.56 then we have kilograms times meters times meters. So we have kilograms, meters times meters is meter squared, all over what? Second squared, right? So that's what our final answer is. It's 70.56 kilogram meters squared over second squared, or per second squared. Now this unit, kilogram meter squared divided by second squared, is what we call a joule. And we talked about that last week, Joule, and it's abbreviated as just a J. So 1 joule is a kilogram meter squared over second squared. Now, when we think about this acceleration due to gravity, this G factor, you have to think about it this way. You've got the side of a building or a cliff, and here's this guy up here on the side of this building, and they are going to jump, okay? So basically, the acceleration due to gravity is that for every second they go faster as you drop toward the earth. And so the first second they drop 9.8 meters. So the very first second they go that far. Now the second they drop an additional, not only do they go 9.8 meters, but they go an additional 9.8 meters. So the second, or second number 2, second is that they drop the 9.8, but an additional 9.8. So that second, the second that they're dropping through the air, they actually drop 19.6 meters. So you add these two. The second they drop additional distance. And then can you guess what happens on the third second? Well, the third second, assuming that we have room for that, they drop additional meters, another 9.8 meter per second. So they're going to be dropping 29.6 meters the third second. And so that's the way it is. It's in other words, they're going faster and faster and faster as they drop through the air. And that's what this meter per second squared is all about. Okay, this unit here. That's saying that's how many meters, and those that constant 9.8 meters per second is going to get added again and again and again for each second that they're dropping. It's added, so it's a bigger and bigger speed that they're dropping as they go through the air. Let's take a look at another example. Okay, and for this one, we're going to take a look at kinetic energy, because kinetic energy, to figure that out, what is the actual kinetic energy of a moving object, not one that's potential energy, it is going to be 1/2 times the mass of the object times v, its speed squared. That's the kinetic energy. So let's say we have an example to give us practice with this idea. Our example is we have a 3 kilogram rock, and we decide to throw it across a river. Okay, and so we throw it, and we throw it at a speed of 25 meters per second. That's a pretty strong throw right there. Okay, so what would its kinetic energy be? Well, we would say the kinetic energy, we always write this as an equation, so you should also always show it as an equation. Put the kinetic energy is equal to 1/2, and what is the mass? The mass is 3 kilograms. So let's put that one in here. There's the mass. And then you multiply that by the velocity squared. And so the velocity is 25 meters per second. And you square that whole thing. It's the velocity. This is the velocity. 25 meters per second. And then it's squared. Okay. So you want to remember to do that. Now, let's go ahead and work it out. The kinetic energy, and you always keep it in a equation form, is 1/2 of 3. 1/2 times 3 is 1.5. 1.5, right? So we have 1.5 kilograms. We just did this first part of the equation. 1.5, 1.5 kilograms. And then we're going to times or multiply 25 meters per second squared. So what is 25 times 25? That's what you do when you square something. 25 times 25, you work that out, and it's going to be 625. So 25 times 25 is 625. Okay? And then, because it's squared, you square the units. So it's going to be meters squared over or per second squared. So you square both the numerator and the denominator, because the whole thing is squared. You see, the whole thing is the unit for velocity. Now, what we do is we multiply these two numbers. What is 1.5? Now, of course, we always show it as a equation, 1.5 times 625 is going to be like 625, and then another half is 312. So it's going to be somewhere around 937. So we actually do the math and we get 937.5. Okay, that's pretty close. And we get kilogram, right? You have to put the units in, so it's kilograms times meters squared all over seconds squared. And what do we remember about that unit from before? A kilogram meters squared over seconds squared is the same as a joule. Okay, so we have 937.5 joules. The kinetic energy is 937.5 joules. Okay, so just multiply it through, use your algebra, just do it the same way every time and you'll be good. Now last week we also talked about momentum. And we said that an object that's speeding down the road has a momentum, like a big truck has more momentum than a small car. So the momentum is dependent on two things: the mass of the object as it speeds in a direction, and then there's a velocity that it's going. So momentum is going to be mass times the velocity. Okay, so it's kind of easy. Now there's a Greek symbol, rho, which we use for momentum. So we say rho, the momentum, is mass times velocity. So if we had a truck, or let's say, let's not use a truck example. Let's say we're throwing a spear, and the spear is 0.5, it's a half a kilogram. Okay, and we're throwing it at 20 meters per second. So the velocity is 20 meters per second. Okay, that's pretty good. That's a pretty good speed. 20 meters per second. So what is the momentum? Momentum is going to be the mass, 0.5. Always put your units, kilogram. And then you're going to multiply that by the velocity. And the velocity is 20 meters per second. So the momentum is going to be 0.5 times 20, so half of 20 is 10. It's going to be 10 kilogram meters. Okay, so we kilogram meters per second. Now that is not a joule, is it? That's not a joule. A joule is a kilogram times meters squared over seconds squared. So remember what our joule unit is: kilogram meters squared over seconds squared. This does not have a special term. We just say the momentum is 10 kilogram meters per second. Okay. Now, this gets really important when you look at braking speeds, and like you're driving a car, because you can stump on the brakes and the wheels stop turning, but the car continues to move forward because there's a momentum. It's going at a certain velocity. So let's take a look on page 276. Flip over to 276, and we get this interesting momentum passage. It says stop. So we're going to read this real quick. The kinetic energy of a car must go somewhere when the car stops. This energy is normally converted to heat in the brakes. If a car comes to a skidding halt, some of its energy is also converted to heat on the tires and on the road. So one of the things that we see is we get friction. And friction would be heat on a surface that is affecting the speed. The friction is this resistance on the surface. That's probably a better way to put it. It's resistance on the surface. And it often changes to heat. So here's one of our heat changes, okay? And you guys know friction will slow down things, right? So let's continue reading. The U.S. Department of Transportation has conducted extensive tests to determine the distance standard passenger cars need in order to stop on a dry, clean, level pavement. The results of these tests are given in the table. The driver reaction distance is based on a reaction time of 0.75 seconds. Though the reaction time stays the same at all speeds, the driver reaction distance increases in direct proportion to the speed. In other words, if you're going faster, more ground will be covered during your 0.75 second reaction time. The braking distance is the distance needed to stop once the brakes are applied. Researchers found that when the speed is doubled, the braking distance is more than quadrupled. So in other words, when you're going twice as fast, your braking distance quadruples. So it takes longer distance, of course, to stop at a higher speed. But when you double the speed, you quadruple the braking distance. This dramatic increase is caused by the fact that doubling the speed quadruples the kinetic energy, coupled with the fact that automobile brakes work less efficiently at high speeds. Adding the driver reaction distance to the braking distance gives the total stopping distance. Stopping a car requires more distance than you might think. The figures given here are for ideal conditions. The stopping distance can be much greater when the car is going downhill, when the weather is bad, or when the road is dusty, wet, or gravel covered. Okay, so we have this stopping distance that increases dramatically. Let's take a look at the speed at 20. So on the chart, at 20, your driver reaction distance, in other words, you're going to travel 22 feet in 0.75 seconds. Okay, that's your reaction time. So the braking distance is, it will take a range, and the range is between 18 to 22 feet to stop the car. So when you add that 18 to 22 feet plus the reaction distance, you're going to get a total stopping distance needed of about 40 to 44 feet. Now notice that when you double your speed, let's double it to 40. Look at the one for 40 now. It's going to take 44 feet to stop the car. That's the reaction distance. That's how far the car goes while you're reacting to it. And then an additional 64 to 80 feet to actually brake the distance, the braking distance. So when you add the braking distance plus the reaction distance, you get 108, somewhere between 108 and 124. So by doubling, and I'm going to write this on the page here, by doubling from 20 miles per hour and then doubling that to 40 miles per hour to stop, all things included, the 20 miles an hour, it's going to take you 40 to 44 feet to stop the car. But if you're going 40, double the speed, you would say, well, that must be double the distance. No, more than that. 108 to 124. So if we go up to the higher figure, at 20, it's going to take you 44 feet to stop the car. At 40, it's going to take you 44 feet to stop the car. So notice you're going up, almost tripling there. It's not doubling, it's tripling. Now, let's look at a second one, and you can kind of see what happens, because it gets worse with the higher speed. So if you're going higher speed, let's say you're comparing between 40 miles per hour, and we're going to compare it to 80 miles per hour. Okay, so at 40, the amount of braking distance plus to stop the car plus your reaction time is somewhere between 108 and 124 feet to bring the car to a stop. But now notice at 80, it's 422 upwards to 506 feet to stop the car. So at 80, you go from 40 to 80, you're more than doubling, you're more than tripling. You are quadrupling. You're from 124 to 506. That's 4 times, a little bit more, a little bit over 4 times the distance. And part of that's because of the momentum. You're going much higher, a larger momentum, a higher momentum, but also you have the brakes that are not working as well at a higher speed. So the brakes build up heat and they slip a little bit. So yeah, you got to be aware of that. So momentum is an interesting thing. Let's look on page 277. Now momentum is also conserved. So as you look at these 3 scenes here, where you have one ball on the top scene, if one ball is rolled in from the left, and it's rolling from left to right, and it hits this group of 6 balls, the momentum of the one ball coming in from the left transfers through to the 6th ball, and you see that 6th ball leaving off to the right. So you can see the momentum is transferred through. If you use 2 balls, like in the second drawing, you have 2 balls coming from the left, 2 balls leave from the right. The momentum is transferred. So there's a conservation of momentum. Now the last one shows, the last diagram shows that you've got, I think it's 6 balls there. Actually 7. You have 7 balls that are coming in, and it's hitting 6 balls. So what happens when 7 balls slam into 6 balls? The momentum transfers, and you can see one of the balls comes off the group of 7 that's coming in from the left, and it leaves with the 6 that are going to the right. So 7 come in, 7 leave. There's a little transfer that happens there, and so we see that momentum is conserved. So we need to be careful of that when we note the importance of conservation of momentum. So we're going to stop at this point and mention to you, now that we're at the end of chapter 12, we're going to be moving into chapter 13 and 14 next week. And for this week, however, you do have a hydrocarbon test. So the hydrocarbon test was an attachment. So be sure to print that out during the week. Take the test. Of course, study your notes first. You can study, even until next week. You can be studying just the hydrocarbon notes. Learn how to name the molecules. be able to draw molecules, like draw octane, octene, octine, cyclooctene, cyclooctine, cyclooctane. Kind of practice. Make sure that you can draw these molecules. Then take the test. Have your parents sign it that they monitored the test. They were there or just close by in the next room. They know that you did not receive any help. You did not look at your notes during the test. And then you should staple the test and mail it to RGES. So please do that. And we will see you next week. There's a little less work today because we are figuring you have a test to take as well. And so we want to give you that extra time. Plus, we usually reduce a little bit the work that we do these several weeks while many of you are taking the history and you have an additional assignment with the research paper. And the research paper is, of course, picking up in its work. So there's a little bit less work. We try to make it a little easier for you to get that research paper in. Now, earlier in the year, you probably remember, we had the science fair project, and you guys did a lot of work at home with the science fair. We reduced the workload at that time, and we also reduced a little bit of the history work for those of you who are taking the history, so you could put a little more time to your science fair project. So it all kind of washes out in the end, and I hope you guys have a good time putting that together and doing well on the hydrocarbon test. God bless you.